Hello everyone, it is a great honor to share this paper here today. This paper is called RAP, a lightweight application layer device against website fingerprinting, and its main contribution is to propose a lightweight application layer device method, RAP, which can resist counter web fingerprint attacks with very low data and latency overhead. Today I will share this paper from the following three parts: contributions, device system design, and evaluation and discussion. As we know, the problem of information linkage in network security has a long history. In order to conceal a user's location and usage from anyone conducting traffic analysis, TOC can realize anonymous communication through a global voluntary coverage network, composed of more than 7,000 relays. Due to the emergency of web fingerprint attacks, TOC cannot realize anonymous communication. In order to protect users' privacy, we propose this method. They are our main contributions, including the following three aspects. Firstly, we design a lightweight web finger device method RAP, which is based on randomizing the request order and the location of website resource. Secondly, we explore several traffic randomization strategies that can serve as candidates for adoption in our device. Finally, we conducted an extensive analysis to prove the effectiveness of our RAP device. This picture describes the threat model. Look, we assume that the adversary can connect traffic in the user's network agent and can deploy a local network environment similar to the user's. The traffic generated by the adversary's own website and the user's traffic obey the same distribution. The adversary has enough resource to connect a large amount of data and has strong computing power to train the classifier. Web fingerprint attacks usually correspond to a supervised machine learning classification problem. After defining a set of websites to be detected, the adversary collects the traffic sequences loaded on multiple pages of each website in the same scene and extracts the web fingerprint that can create the websites. Adversaries can use machine learning or deep learning to train classifiers to identify website categories. We find inspiration from the Xidian network. The network tracers obtained by simultaneous casting the Xidian websites in different regions may be different, which will case the web fingerprint classifier tried in one region to seriously reduce the accuracy of classifying the traffic collected in other regions. Our defined makes toll users with each website just like visiting a Xidian website, and adds other random factors to the HTTP request so that the loader tracking of the same website is different every time. In order to defend against web fingerprint attacks, our defined system makes the traffic sequence generated by users visiting the website more on concert. Our defined system is composed of volunteer OR nodes that make up the Tor network, Tor directory service, and user agency, as shown in this picture. Defining preparation in advance, building the corresponding relationship table between website resource and ORS and schedule resource. After we have determined the connection of website to be defined by web fingerprint, the Tor directory server will visit the website in the connection one by one, recording the GS resource object, CSS resource object, and logo image objects that are not easy to change. The Tor directory server reads the list of Tor ORS that are waiting to provide defense and building a table of correspondence between website resource objects and ORS. The selected Tor nodes star HTTP service become an HTTP server and regularly obtains the correspondence table from the directory server and finds items related to item itself in the table. The Tor resource server downloads the web resource object from the original HTTP resource, rename the fields according to the table information, and saves it to its own HTTP server. Look like this algorithm. It is very important to establish the corresponding table in the above steps. To the following is the algorithm for establishing the corresponding table. The main challenge of our defense strategy is to make the load tracer of the same page highly different to prevent the adversary from finding fingerprinting partners. We analyze the influence factors from three aspects: serve, transmission path, and client. After we determine the size of the website connection, we can obtain the website source code and obtain the number and the source of all the resource fields that need to be stored on the Tor nodes. We analyze the traffic randomness of the number of parallel 3-hop circles used to set requests and receive responses. We analyze the impact of different HTTP request allocation strategies on multiple circles on the traffic randomness. We evaluated our defense method through experiments. The following are the experiment steps and results. Firstly, we can collect the experiment data. We deployed our defense system in the real Tor network environment. We collected a new dataset between September and November 2020 using Tor Bronson 10 with a configurable SSR proxy. Secondly, we classify and evaluation our method. We consider for state-of-the-art web fingerprint attacks such as KN, CUM, UL, KFP, and DF. The experimental results show that accuracy of state-of-the-art web finger attacks in without defense and agency our simple traffic randomization strategies As shown in Table 1, we performed simple multiples defense experiments in the SSR-TOR DS dataset, which means that we set the complete HTTP request via 5 circles based on the round-robin method. Look this picture. The experiment results show the accuracy of state-of-the-art web finger attacked under different resource visuals and circle numbers. We performed some experiments to determine the influence of resource proportion on the DSDF dataset. When P is 0, the order of HTTP request is disrupted and the requests are sent to the origin website through multiple circles using the round-robin method. The result is shown in this picture. Those experiment results show that our method is significantly better than the existing method in latency and data overload. In this paper, we propose a net-wide application-level RAP device to protect against web fingerprint performed by proposed adversary. RAP is based on the idea of Xidian, where web objects are placed on the toe node. Clients obtain HTML files from the origin site, or HTTP requests are obtained and sent through multiple toe paths. Some requests are sent to the toe node instead of the origin site, and additional HTTP requests are added to confuse traffic during the initial state of visiting the site. Because RAP is a defense acting on the application node, it has scalability and compatibility in through. We analyze the traffic randomization scheme and determine the optimal system parameters. We show that our RAP device is able to reduce the accuracy from more than 98% to 14% for all state-of-art attack, with only 31% latency and 13% data overnight. Our device system does not need to modify the underlying toll network. Therefore, RAP is suitable for deploy in toll. Thanks for listening.